one of the goals of my research and how the research that I do fits in with the overall scheme on the topic of asteroid families. And then I'll talk a little bit at the end, or a bit at the end, exactly about the techniques that I'm using to investigate this topic. So I want to review with you a little bit some of the history of the solar system that set up the initial conditions for the main belt as a ground slate for the conditions in which I am investigating the main belt for asteroid families. It is at the onset of the creation of the creation of the solar nebula and the settling of solids masses into a coherent disk. There was very early migration during the gas lifetime of the disk of the giant planets, and at this time the incipient main belt was scattered by the migration of these gas giant planets and to values that it was excited to the same extent as we see the asteroid belt today. And this is known as the Grand Attack from Wash et al. 2011. But the key issue here is that we had this dormant, initially the main belt was dormant, and then by the migration of the Jupiter and Saturn, it was excited and depleted to values to the level of excitation, to approximately the level of excitation and depletion that we see some of today. And this cannot be the level of excitation of the main belt cannot be explained solely by the disk profile, the profile of this disk, and that you have to evoke this mechanism of migration in order to see the conditions of the main belt that you see today. And this is a recent result by Isidoro et al. That investigated this, that looked into different disk profiles and whether or not they could reproduce the conditions to set the groundwork of the conditions that we see in the main belt today. And so about the disk lifetime was, and the initial migration of gas giants that excited the disk occurred within the first 10 million years of the solar nebula condensation when the gas was still present. But 20 to 500 million years after the formation of the solar system, there is this event known as the early or late instability, depending upon when it occurs. But the constraints on which we, the observational constraints on which we indicate that are indicative of the late instability, do not really depend upon can depend upon a wide range of dates for the actual occurrence of this event. So this is from Saganis et al. 2005, where he measured the change and the orbits from circular orbits to more eccentric orbits and a steady outer migration of Jupiter and Saturn until they reach a 2-to-1 commensurability in their orbits, which is affected by the angular momentum exchange with an outer disk, a massive disk of planetesimals at 35 AU. That is on the order of the same mass as the mass of Jupiter. And with this result in mind, Gomez et al. Ran a simulation and was able to determine the timing of this event was coherent with the timing of the late heavy bombardment 4 billion years ago, where this outer disk of planetesimals was scattered and excited by the outward migration of the gas giant planets and had orbits that were sent in on planet crossing, sun colliding trajectories. So a further refinement of this this NICE model was the so-called jumping Jupiter case, where looking into a little bit more scrutiny shows that one of the gas giant planets is ejected from the system in this period of late instability, and in order to mediate that, Nesvorny and Morbidelli proposed that there was a fifth gas giant planet that was excited around the time of this that was excited and ejected from the solar system during this outward migration period. And in each of these cases, 1, 2, and 3, the black and red lines are Jupiter and Saturn, and the remaining gas giants, the 4 remaining gas giants, are the 3 remaining gas giants are represented by these green, blue, and cyan lines. And in all 3 of these cases, one of the middle gas giants is excited, and actually has excited enough to where it can actually penetrate the main belt. And this has a consequence in several respects to further exciting and depleting the main belt. As you are having the migration of these gas giant planets, you have the location of resonances that are changing and are sweeping through the main belt. And with the penetration of a gas giant, you also have close encounters with asteroids that can scatter their orbits. So the effect that it has on the main belt, in terms of depleting and exciting it, to the current values, is a refinement on the initial conditions of the main belt before the late instability caused by the Grand Tack model, where basically the level of excitation is directly added, is in addition to what was the level of excitation of the belt before the late instability. And what this means for asteroid families is that if you have these close clusters of these close dynamically significant groupings of asteroid families that are dynamically groups of asteroids known as asteroid families that are dynamically associated with each other, the shifting resonances that are changing due to the migration of the gas giant planets, as well as the penetration of a gas giant planet into the main belt, causes scattering in the orbital elements of these objects such that they cannot be recognized, such that the families cannot be recognized. So what this means is that if it is true that we had the penetration of an additional gas giant planet into the main belt, that asteroid families before the late instabilities are not recognizable. So what this means is that the framework for which I am investigating which I am searching for asteroid families, or investigating the formulation of asteroid families, are those asteroid families which have been created sometime in the last 4 billion years. Now, there is some work that suggests that perhaps that asteroid families, that the main belt was at an initial mass that is today, that basically the mass of the main belt has not changed during that time. There was not at this initial massive stage, and that there may have not had been enough material to create these asteroid families starting at 4 billion years ago. But this is a matter of current research which is being investigated. So talking a little bit about the asteroid families, is that these were dynamic groupings that were first proposed almost 100 years ago. And you can see them here in this map, where this is the semi-major axis and the inclination. On the right plot and on the left plot, it is also a semi-major axis for eccentricity. And this is where we are taking the association of groups of asteroids to each other, and we are removing all of the background, so that you can only see the asteroid families themselves. And it's very clear that it's easy to recognize on these plots that these asteroids are tight compact groupings. So how asteroid families have been determined is that they are calculated using their proper elements. They calculate a velocity, a relative velocity between fragments is calculated, and the distance between the difference in velocities between the center of a cluster, the center of an asteroid family, and its members is increased, and until the level at which you get quasi-random groupings of asteroids from the background main belt is too high for the group to be significant. And eventually you get to a point where you basically include the entire main belt as you increase this relative difference in velocity between fragments.
Is that really meters per second? 3 meters per second?
Velocity of cutoff.
I think.
Yeah, you are. Yes, you are right. It should be meters per second. This is from a review paper that takes the work from Zapala et al. But it's not kilometers per second. It's actually meters per second, and it's kind of an abstract quantity where you are using these equations which take the orbital elements themselves to compute, say, if the fragments were to break apart, at what speed would they be spreading apart? So it's not 150 kilometers. I apologize. It's meters per second.
The interesting solar system.
So the asteroid families are created in disruptions, and lots of work has been done that suggests that the progenitors of asteroid families are reaccumulated masses of disrupted asteroids, and where the asteroid was initially broken up and then reaccumulated by gravity and then broken up again, and that the fragments that's reaccumulated by their self-gravity before reaccumulating to a larger mass again were the progenitors of the actual fragments, of the larger fragments of the asteroid family. And then you get some debris that follows a power law that are smaller as you decrease the diameter past these accumulated fragments in the original parent body. So how the global collision rate at which you would expect asteroid families to be created has been modified since the late instability, but has since then remained mostly intact. But around 4 billion years ago, earmarked by this period of late instability 4 billion years ago, there, as seen on the rate of creation of craters of the moon, there was a steep increase followed by a steady decrease starting 4 billion years ago. And since then, there is not the rate at which collisions the rate at which collisions occur globally within the solar system has remained relatively constant, and this is a consequence of the steady state of the architecture of the solar system since 4 billion years ago. So since the collision rate has remained constant for the last 4 billion years, we can expect the rate at which asteroid parent bodies are disrupted that create asteroid families is consistent with the size of the parent body. So if you have a 100-kilometer object, we would expect it to have a collisional lifetime, or somewhere in the solar system where an object of that size is being disrupted once on the billion-year timescale, where you would have smaller bodies being disrupted much more frequently. There is some research that suggests that primordial family or older asteroid families, the older the asteroid families, the larger the parent body has to be. But it is not exactly clear if the comminution rates in the solar system precludes the possibility of there being older asteroid families, it precludes the possibility of there being an anti-correlation with age and parent body size. But we can assume for now that for the last 4 billion years that there should be a steady rate of creation of asteroid families, regardless of parent body size, over this period. But when you look at the distribution and ages of asteroid families, you see from the latest work on the ages of asteroid families by Federico Spoto, there is not really a uniform distribution in the age. So we get a bunch of guys that are just under 1 billion years ago, or around 1 billion years ago, and some younger families, and only a few families that are between 2 and 3 billion years old, but nothing really beyond that. There's one of the oldest families, Ursula, has a central age value of 3.5 billion years, but the error bars on it are significant enough that it could actually not be that old. But also complicated by this fact is there's some recent development on the way in which asteroid families are actually aged, where they could actually all be younger. So it makes it even more puzzling why there are not more known asteroid families with ages that are exceeding 2 billion years old. So could this be due to biases in the method used to age families, or possibly biases in the method used to define families? If we look at the distribution of young families, there is some possibility in that, because if you have a young family, the fragments have not had enough time to become diffuse enough, or they have not spread out enough to be recognizable above the background, or they could actually be too small, too little material to be to have for there to be a significant detection. Where for old families, I'll get into some of the more difficulties why that's more related to the topic of my research. But it seems that somewhere in the middle, the method is more robust, or there's less of a bias towards detecting objects against objects that are intermediate in age. And so some of the reasoning for this, for why this occurs, is that particularly in focusing on the inner main belt, is that you have these diffusive effects on the orbital elements of the families, which are used to calculate the dynamical association between bodies. And so this is a work by Andre Milani from 1994, where he studied the diffusive effect of the perturbations on the bodies in the Veritas family, and he found that on even just 10 change in the orbital elements E and I on the inclination, on the eccentricity and the inclination on the asteroid family, such that you could have family members that would not be dynamically associated with this group. So you actually had to integrate the orbits of these bodies in particular to see if they were dynamically associated. So if you were to look for this family a priori without knowing without taking into account this chaotic diffusion, you would not be able to associate these fragments with the fragments of this family with each other. And so you also have this case of where mean motion resonances and secular resonances are present throughout the inner main belt and other areas within the main belt that have the capability of increasing the eccentricity and inclination of these objects. So you have, for particular mean motion resonances have a eccentricity dependency on where the boundary of chaoticity is present in the proximity, which can affect the orbits of these bodies, exciting them to where, if they were initially could be associated with each other, that they become too modified and too diffuse to be recognized and attributed to the cloak core of the family. And you also have secular resonances, which are a bit more complicated than mean motion resonances, and the way you define them is they have a much more non-monotonic way of spreading throughout the inner belt. The inner main belt as a function of the inclination of the bodies of the asteroid's proper inclination, and semi-major axes. So work has been done into looking at the effects that these things have on the effects of these resonances on the bodies themselves, and they find that over even just a few tens of millions of years, hundreds of millions of years time, there's a significant deviation from the initial values that they had. So this may explain that, okay, well, we might be able to dynamically associate objects on the hundreds of million year scale to order of magnitude billion year scale, but beyond that, the objects are becoming too diffuse, too spread out by these resonances to be recognized and attributed to each other. And there's also this other case where the non-destructive impacts and close encounters with other asteroids with massive bodies can spread out. They can affect the semi-major axes of the objects. However, the close encounters problem is more influential in the case on a much smaller statistical scale, where the non-destructive impacts can affect more asteroids, but the scale at which they affect the change in the semi-major axis is which is represented by this black line. Like here, this is the mean. This is the scale at which you have the change in the semi-major axis as a function of per millions of years is actually quite small compared to the change in the semi-major axis that's caused by the Yarkovsky force. Now, I will talk about the Yarkovsky force in more detail, as it's more relevant to the spreading in semi-major axis of asteroid families. But essentially, if you have this graph here is a semi-major axis versus the absolute magnitude, where the absolute magnitude is a rudimentary measure of the size of an object. But basically, the Yarkovsky force scales with the absolute magnitude or the inverse of its diameter. And the effect that it has is that if you start from, say, this parent body represented by the star, this is the most massive member of the family, and you go to smaller sizes, the Yarkovsky force has a greater effect and will almost quasi-equally spread out the objects from their initial position and from their initial values in semi-major axis. And this is what we call the V-shape. When I say V-shape identification, I'm referring to this V-shape signature, this V-shape correlation that you see in semi-major axis versus absolute magnitude or the inverse diameter. So the Yarkovsky force is a thermal recoil force that is caused by the diurnal or seasonal heating of the hemispheres of an asteroid, and this has a direct effect on the displacement. The rate. This has a direct effect on the orbits of the object. The diurnal effect, where you have an object rotating with its rotation pole more perpendicular to the ecliptic, is much stronger than where the seasonal effect, where the rotation pole is more or less perpendicular. This is order of magnitudes higher than this. So when we are calculating the effect of the magnitude of the drift in semi-major axis, it is measured in terms of the ecliptic of the angle between the pole and the ecliptic itself. There is also an effect on the rotation rate of that is very important. There's also effect on the rotation rate that it has on the size of the Yarkovsky force, and that if you have a body that is stationary, you do not have this diurnal effect, and you do not have this recoil, this change, this drift due to the recoil from having from the diurnal effect. And if the object is rotating too quickly, then depending upon the thermal properties of the object, the effect might also be weakened. But you also, in addition to that, if the object is rotating so quickly that it starts to shed mass, it will change the angular momentum of the object, and the rotation rate the rotation state will be different from what it had before it shed mass. So the way in which the asteroid family, the way in which asteroids' rotation rates are modified is called the Orb effect. But going beyond that, just real quickly, it's basically you have these surface irregularities on the surface of an asteroid, which are heated by the sun, and then have this recoil force that is anisotropically re-emitted over the surface of the asteroid that has some net torque effect, that has some net torque on the object, causing it to spin up more rapidly. And this is what changes over time. This is what changes the obliquity and spin rate of the object. The obliquity change, the rate of the change in obliquity, and the change of the rotation rate, depending upon the obliquity of the object. And this has a direct effect on the Yarkovsky effect. It has a direct effect on the sign of the Yarkovsky effect, where if an object is rotating in prograde, it will drift outward. If it's rotating retrograde, it will drift inwards. It will drift to smaller semi-major axis values. So there is an important detail that when talking about this Orb effect is that over time, if you have minute changes to the shape of an asteroid, it's very difficult to see here, but you can see here that this pebble here is no longer present here. And if you just have little minute variations to the shape of an asteroid over time, it can have significant effects on the torque, where this blue line, this red line was the torque, the effective torque on the asteroid before it lost, before its minute change to the shape, and the blue line is the change in its torque. The blue line is the change in its torque as a function of obliquity after the shape has changed. So what this means is that you have as the object, as an asteroid, the shape is changing, possibly due to the alteration in shape due to rotation forces or by non-destructive impacts. The rate at which its rotation rate changes can be so extreme that the status of the effect, the magnitude of the Yarkovsky force on it is always in a state where it is maximized. So if you have the Orb effect that is either spinning up asteroids or spinning down asteroids, if it is causing them to spin down, the Yarkovsky effect will be quite diminished. But if you have this stochastic effect where the change of the shape of the asteroid is resetting the Orb state, the rotation rate, then you will have the asteroid will spend more time in which the Yarkovsky effect is maximized. So I'll talk about what the consequences are for asteroid families in a bit after that. But before that, I want to talk about I want to go back to the formation of families, to the finding of families, where I was talking about the effect of the diffusion and the proper elements of asteroids and their effect on the ability to detect asteroid families. So there is this asteroid family called Eulalia that, using classical methods, could not be found with the velocity cutoff method. So this red box here represents Eulalia, the most massive body of this family. You see that it is quite significantly displaced from what by eyeball would be the median of the values for inclination and eccentricity. So the problem with this object is that even though the difference in scale across all of these of all of the asteroids is minute, it's enough of a difference to make attributing it to itself, to attributing the most massive parent body to its own family rather difficult, where the cutoff velocity above the
above the quasi-random level is much more significantly increased or decreased depending upon the initial eccentricity value of its most massive member. So this is due to the fact that this is due to the fact that over millions of years, the location relative to the 3-to-1 resonance of Eulalia the location of Eulalia relative to the 3-to-1 mean motion resonance of Jupiter is causing its eccentricity to vary extremely, very rapidly. The most present value here is an eccentricity of 0.11. However, if you integrate the orbit of Eulalia in close proximity to this resonance over a billion-year timescale, you find that the asteroid only shares its present value in this location for only 10% of the time. So the rest of the time, it could be in a location where we're attributing this parent body to Eulalia is possible, where other times it is not. It is a matter of a very small random probability. So if you were to do this clustering method, modifying the value of Eulalia, and you use the method to attribute asteroids to itself as one coherent family, you actually also capture this clump here, which plotted in absolute magnitude versus semi-major axis space has kind of this ear shape, where it's been the other half of the ear shape has been depleted by the presence of this 3-to-1 resonance. So this so when I am the method that I'm investigating to find families, in this case where the dynamics of some of the bodies in the family prevent them from being attributed by classical methods, I am looking for these. I'm exploiting the fact that this correlation here between the semi-major axis and the absolute magnitude is preserved even in the case of being within close proximity of these resonances on billion-year timescales. So the way Kevin Walsh did this in his 2013 paper is that he did a search where he modified a value that is a measure of the width of the V shape, of the Yarkovsky V shape, and he calculated the derivative of the number of objects, as the difference of objects along at the border of this V shape as a function of the width of the V shape. And for varying values of the size where this dotted line, the dotted lines are varying ranges of absolute magnitude between 10 and 16, where this black line is the average. He was able to find these two solutions where these two peaks that are more or less the same. And the location of the border here in the semi-major axis versus absolute magnitude space is along where you see this dense clump or this dense ear. And taking the width of this V-shaped value and then computing an age, you get an age of around 1 gigayear. But this is complicated by the effects of stochastic torque, which I will talk about in a bit. And in addition to the asteroids found in the hierarchical clustering method by modifying the initial eccentricity of Eulalia, there was also attributed a second family, which was found in a similar vein called Polana, which before this was thought to be a part of just one family, but it's actually two separate families now. And this has a much wider V shape and a putative age of 2 billion years based on the Yarkovsky spreading. Now, what you're looking at here, these red lines, are the contribution to the V shape as caused by the initial velocity displacement. So when you are calculating the age of these families, there are many complicated factors in which you have to assume some initial mass of the original parent body for the creation of this family, and from that you get an escape velocity. You can calculate an escape velocity, which gives you the idea of the contribution to this V shape, the initial dispersion caused by the disruption of this parent body to this V shape. So if you were to have a large parent body with a large spread, a large initial dispersion, it is possible that you could have the same age as you would have for a smaller parent body, but a smaller spread because the initial contribution to the spread of the V shape is smaller due to the lower escape velocity of an object with lower mass. Now, I was talking about stochastic, the effect of York varying due to the change in shape, small, minute changes in shapes of asteroid, and the effect that this has on the aging of families is that as you get to smaller sizes, or larger values of absolute magnitude, their York states are the V shape doesn't become a V shape anymore; it becomes more of a blob. And so this is a problem. You see here that these curves represent ages from 0 to 2 gigayears. And you see that as you get to older sizes, the distortion that you see due to the stochastic York affects our objects at larger and larger sizes. So for between 12 and 16 absolute magnitudes, while using this formulation for the Yarkovsky V shape. Now this V shape here was found numerically, but a new analytical formulation will have to be devised in order to take into account the stochastic York. But it is not clear exactly how. But it is clearly important because if you want to find families which are older than 2 gigayears, the effect that it will have it will affect the border for objects that are larger than absolute magnitude 16, which constitutes a significant amount of mass to an asteroid family. So the effect that it has here, the effect that stochastic York has in the age of the family for Eulalia is much different from what is found using the classical York models. It's on the order of 1 gigayear. But for Plana, the effect is much more extreme because, as I said, as you get to older sizes, as you get to older ages, the effect that stochastic York has on the age is the effect that stochastic York has on asteroids is also included for asteroids of larger sizes. So if you have this spreading due to the V shape and the border is defined by these larger asteroids, their contribution of those asteroids to the age of the family is going to be diminished depending upon the age of the family. So there's a little bit of a circular argument there. But it will mean that in the future, for finding families that are older than 2 billion years, one will have to use you will have to use body asteroids. We'll have to exclude their data set to either having a smaller, using smaller number statistics, or they'll have to have a formulation for that takes into account this stochastic York effect. So what I've done to find these, to look for these families in a more automated, in a more broad sense, is I've expanded upon the work of Kevin Walsh to do this V-shaped search as a function of the absolute magnitude and semi-major axis. And so I've come up with a few different techniques, but the technique that each technique is different, has different advantages depending upon the possibilities. So one technique is I look for the density. I look for is more sensitive to clumps. So if you look here at the Nisa Plana family, the Plana family here and the Eulalia family here, is that there is a clear border right here, but there's also this it's called higher density of objects in absolute magnitude in swim major axis space. And so what the density method does is that it looks for these more denser clumps. Mm-hmm. And the advantage it has, it's kind of biased to lower values. And C, the value in C that Kevin Walsh found was 9. Well, the value that I find is around 8.5. But that makes sense because Kevin's method is more is looking at the border, is more sensitive to the border, where mine is going to be more sensitive to the center of mass of a clump, which is going to have a smaller V-shaped profile than to the border. But in some other ways, the border method is less capable of finding these objects where you do not have a clear, you do not have this clear abscess here. So this is kind of a special case where you're able to cut the data set down to where you can see basically this nice border right here. But in most cases, when searching through the asteroid belt, and I'll talk about this more in my paper when it comes out, but in more cases throughout the asteroid belt, there's actually just a distribution of a consistent background that spreads out throughout the swim major axis through absolute magnitude space, and you cannot exploit this border method. But as we've mentioned before, is that the border technique is more sensitive. It seems to be more accurate for finding the actual to determine the actual border if you have this like an abscess that's exterior to the V shape. But it is significantly less sensitive to asteroid families, which are contained within that are surrounded by this background of asteroids. And so you actually see that. Oops. So you actually see that in Kevin's method here, is that that these peaks here, there's not you don't get a consistent solution. You have multiple possible solutions that are a function of that could be stronger depending upon the size of the asteroid that you're using, because the Yarkovsky effect has a different the rate at which objects are displaced by the Yarkovsky force is different depending on the object size. So this is an overplot of the solution of the fits that I find for the Bolana and Eulalia family. And kind of highlights the way the method is working. Where I search for where I'm calculating the derivative or the density within an envelope of possible V shapes. But this technique is kind of in development and work, and has a little bit of ways to go before it is finalized for publication. But that's it for my talk now.